So I wanted to talk to you today about our pipeline for large-scale geospatial analytics, because it was really amazing to me to come to Max Point and find that, oh, we can do all these things basically with the Python stack, and it can be done relatively quickly. I mean, like, we had the idea for this project and kind of had the data streams, a lot of the data streams already there, but to actually build the product took, a handful of people, like a few months. Obviously, we're improving on it since then, but we had something up and running that we could deliver to the market very quickly because of the capabilities that we have with Python. So I wanted to give you a little overview of my talk before I get into the details. First, we'll go through the problem, solution architecture, the tools we used, data manipulation, the data flow, how we get from geocoordinates to point of interest data, and how we can measure changes in visitation rates to our points of interest, as well as co-visitation rates. So that being, I have a place I want people to visit. Where else did they visit as well? Where did the people who visited my place, where else did they go? And also some cool aggregate statistics that we came up with for some neat insights. So the basic problem that we have is transforming raw GIS data into points of interest. So into visits into points of interest. So basically you have some lat-long data and you want to know, is that like somebody going to a place or is it just somebody hanging out in a parking lot? So Max Point receives tens of billions requests a day. We're a digital marketing technology company, and we receive requests when like your page loads in your browser or on your app, and it wants to give you an ad, then a request will come back to us. And if you've chosen to share location, we can get that location data. So we receive many requests for giving us location data a day. And we need to filter these down so that they're geolocated and have sufficient quality. And then we want to match these geolocated points to points of interest and provide useful insights to our customers who want to know, okay, I served this ad campaign. Did people actually come to my store? And they also want to know what sort of people respond and what sort of other places they visit in addition to their stores. So again, the basic idea is going from something like this, some lat-long coordinates, to something like this, stores that people actually visited. And this is a generalizable pipeline. You can generalize it to your favorite study organism or machine. All you need is something that's sending back location. So to emphasize this, I chose a wonderful organism, cats. And I will be using that as an analogy throughout. If you had a bunch of cats and you gave them radio collars and they sent back location data, they would be just as good for this pipeline as people. And even better, because if we tag them with radio collars, they would have a hard time taking them off, and they wouldn't get to choose whether they sent it, whereas people may decide not to choose to send location data. So the basic architecture. I'm going to be using this slide throughout the talk to kind of orient you as to where we are. But the architecture for this solution is we've made it modular so that everything's separated out. You have the UI where we can make requests to our system and ask for studies, a load balancer that allows people to multiple requests to be made at once. There's a section with core computations where we do all the analyses, as well as a data access layer that pulls back the data from the cluster, and then our clusters that include the geolocation data, the point of interest data, as well as metadata about users and locations. So that's our basic architecture. Now we can overlay the tools that we use on the architecture as well, and all of these are basically tools that can be used within a Pythonic stack. So we use Flask for our UI. and Celery for the load balancer. And core computations, well, we have many things that we use, but all using with Python, really. We use scikit-learn and pandas, and we use Impala and Spark with Ibis and PySpark. And also the data access layer, again, is with Ibis and PySpark. And our data in the cluster is stored within Hadoop. So for the UI, again, obviously this is a very bare bones UI. It's more of a prototype, and we wanted it to be that way. We wanted to develop something quickly and take it to market. So we developed this very quickly within Flask and Celery, and now we have something where someone doesn't have to go and program anything to request an analysis. They can go in and say, I want to know for this advertising campaign, for these dates, what happened with visitation to my stores. So this is an internal UI, so it doesn't have to be fancy, and it allows us to get things out very quickly. And so we were very happy to have Flask and Celery to allow us to quickly make this UI. Going into data access and some of the core computations, we're using Impala and Spark for that. We really needed something that could be fast and handle large-scale data. So Impala is fairly fast over here, but it's designed for shorter running queries, and we found kind of prone to failure for longer running queries that it wasn't designed for. If we want a large amount of data with lots of computations come back to us, Impala is not that reliable for that use case. And so we learned something, and we're moving over to Spark because it's fairly fast. It's not as fast as Impala for some things. It's sorting on disk, which can slow things down for large data sets. But it's really stable. It handles larger queries more stably, and that's really what we need. We need to be able to send out a request and get it back. It's important. So we also wanted to use Impala and to use Spark in a Pythonic manner. So we use Ibis and PySpark. We wanted things also to be modular. We wanted them to be maintainable. And we didn't want to have lots of long strings throughout our code like we'd have with SQL. So Ibis and PySpark have very similar syntax. They're intuitively similar. On the surface, their expressions are similar, but so you write out an expression. It has to be executed to pull back the data and to actually run the computations. There's differences in the underlying mechanisms, of course. Ibis is accessing through Impala. PySpark goes through Spark. And again, there are differences in strengths and weaknesses of Impala and Spark. Impala you would want to use for small, quick jobs, and Spark for larger, more stable jobs. So Spark is ultimately for the amount of data we have and the amount of computations we want to do on it the way that we're going. So I just wanted to give a quick example of what the code looks like, and it's not really that visible on the screen, but the basic idea is that they have very similar syntax. You reference your data, you can do joins, you can do selects and filters, and then you can execute your statement and for each of these. So you end up with something in Python that goes out to your cluster and executes the statement and brings you back data. So very similar syntax for both. So onto our data flow for this. Again, the basic operation that we need to do is take device coordinates and point of interest data and turn it into, okay, I see this device at this point of interest. I see, for instance, if I was trying to attract cats to my house, I see a cat at my house. Or I see a person at the store that I want them to go to. Or maybe I see them at a different store. So that's really the central component of this data flow. We really, if you have a device at a point of interest, you can go many places. So you might, after you have devices at points of interest, you might want to administer some sort of test and have some sort of control so you can see if your treatment worked. For instance, I might administer advertising to get people to go to my store, or I might put out some food to get cats to come to my house. I really miss, when I moved, I don't have stray cats near my house anymore, and I need to get some. So it's important. I enjoy them. So we can score devices on metadata, whether that's any data that you have about your organism or person, and create a lookalike control. And then you can measure a visit, a visit treatment effect. Also, once you have a device at a POI, you can go to have co-visitation with your target location. So we can look at, okay, cats come to my house, they come to my neighbor's house, where else do they go? And then you can also get aggregate statistics if you have device metadata on the visitors that came to whatever point of interest you're interested in. So I'm first going to talk about taking device coordinates and point of interest data and going to a device at a point of interest. So we tried two different methods for this, for location encoding and matching, to get from that device location to seeing the device, to knowing that device is at a specific place, not just a lat long, but at a store within whatever shape you have for your POI, basically. So we tried R trees and geohashing. And the basic idea for an R tree is that you group different locations together and map your point within that. Whereas geohashing takes locations and sends them down to a one-dimensional representation using a z-order curve. And so we're starting out with R trees and finding that geohashing is really much better for the scale of the data that we have because it scales much better. As you add data, it doesn't degrade as fast as an R tree. So that's really, if you have really big data, geohashing is really the way to go, we've found. So now that we can match a device with its lat long to mapping it to a point of interest, let's go on to talk about making our control group. So let's talk about a different type of hashing. So we were talking about geohashing before, but this is more hashing IDs for users. So if we have a test group, we basically want to create a lookalike control group. And we can score that control group on different metadata, and we can match it to the test group. But if we have tons and tons of control user pool, we really need to do some subsampling there, and that's where the hashing comes in. So hashing is a way to reduce our computation time and do some subsampling by just basically taking a basic hash of your choice that has basically a uniform distribution, and so hash your user IDs and use a modulo operation, and you can do a uniform subsample so that you don't have to use every single person in your potential control pool. And you can also uniformly sample throughout a distribution that you want to have in that pool. So once we have a control group, we can do all sorts of different measures. We can measure traffic lift. We can compare the control to the test group and say, how much lift do I have in my location? How many more of the test users are coming to, or how much are the test users more likely to come to the store than the control users? You can talk about repeat visits and compare it between the test and control users as well. You can say, well, I have, my test users are more likely to come back to the store at this rate, and the control users are at a different rate. So you can tell a story there. You can also compare their visitation over time. And these are basic aggregations after you have your test and control group that you can compare. So now let's talk a little bit about co-visitation, what it is, how to get it. So the basic idea of co-visitation is that other locations that our users visit might be important too, not just my house, but hey, the cats might go to the orange house and the blue house down the street. And, I'd rather them be at my house, but I'd like to know where else they go. I can identify these cats with their interests and and my competitors. Like, I don't, this orange house, it's a really huge competitor of mine. All the cats are there. I can identify their visitation patterns as well. Maybe they go in a certain order to these locations, or they're likely to go to certain places on the same day. Maybe these cats have a migration pattern, kind of like cows, and they go one place in the morning and somewhere else in the evening. So that's the basic idea of co-visitation, and it's basically just aggregating up your data again once you have your devices at some point of interest. So now we can get into some interesting other aggregate statistics for visitors using the device metadata that we might have. So one thing that MaxPoint is known for is having neighborhoods. So one thing we might want to know is what are the neighborhoods that people are coming from to my store or my chain. And so you can do some aggregation and figure that out, but you might want to have a heat map like we're showing here. And to do that, you need to do some sort of binning. And we found here that a basic Q-cut in pandas isn't going to work because of the distribution of the data. We have a really long tail. So we ended up using scikit-learn and k-means clustering, and then we could have our high, medium, and low bins and visualize them on a map like we have here. You could use Tableau. You could use QGIS, whatever your favorite visualization thing is that can handle large amounts of data like we have here. So yeah, so k-means was another lesson that we learned here with our long tail there. It worked much better than the Q-cut. Another aggregate statistic, how far are people traveling to the store, or how far are cats traveling to get to my house? So distance traveled metrics, and then we can put them in bins and say, oh, a lot of people are coming from 10 plus miles, or a lot of cats are traveling 10 miles to get to my house. I'm important, that would be good. So when you're doing distances, over long distances, you need to choose an appropriate ellipsoid because the world is not exactly a sphere. It's not exactly round. It's also not flat, so neither of these are acceptable. You need to choose the appropriate geodetic system and the appropriate ellipsoid. So different ellipsoids are useful for different purposes, and again, it matters with long distances. So we used PyProj for this in case people were traveling from really far to our stores. And the system that we're using is WGS84, which is a pretty standard system to use, and it works well in many cases. Then we can just do a basic distance calculation and then do our aggregate and have our insight for our customers. So now it's time to take these tools to learn more about cats or whatever you would like to learn about. So I've presented a pipeline to convert large-scale geocoordinates into insights. I've given a flexible architecture that has interchangeable pieces. Again, everything's modular. We're able to switch out Impala to Spark. And Pythonic tools for UIs and data access, analyses to create useful insights, as map geocoordinates to POIs, and developing a control with big data with the hashing, as well as clustering with k-means clustering, and computing distance algorithms. So thank you for your time. We can take any questions now.
Why ellipsoids as opposed to some other geometric shapes like polygons?
They fit the Earth better. So the Earth is not some other random polygon. So, I mean, unless there's a polygon system that you know of, are aware of, that I'm not for mapping the Earth. It's what's standardly used. Like WGS 84 is basically what is used in your GPS mostly. So.
I'll talk to you later.
Okay, cool.
Hey, how do you handle different levels of resolution in the GPS data? It could be, a little bit higher or lower depending on the device or other conditions.
Yeah, so basically we have to filter out things that are of bad resolution. We have to look at it and say this is not accurate enough for our purposes, or this appears to be snapped to a location that may not really be where the device is. So lots of filtering.
Can you give us a sense of the scale of the geocoordinates in the sense of number of locations total per day, order of magnitude? How large is the geospatial database? You've got to look at somebody else.
Do you know, Marshall, how many geolocated points we get per day? This is unknown. I know we have billions and billions of points, and then a lot of them are geolocated, but I can't tell you exactly how big, yeah.
So you said that you moved kind of from Impala to Spark. Was it a replacement, or do you use both, and do you still find a place for Impala in the stack?
So for this product, we are not quite completely over to Spark, but we want to get there as fast as possible, because it really, with this.
Is there anything that Impala buys you that you aren't getting with Spark?
So I really like the speed for fast queries, and I think it buys us that. I've noticed when I want to just get something back, it brings it back quickly. Part of that is, though, that people in our company are all moving to Spark a lot, and so that slows down our Spark cluster. But part of it is that Impala really is designed for quickly those small, fast queries. So it's really good for that sort of small exploratory stuff. Yeah.
There are two questions over here.
Yes, you showed earlier a user interface for end users. Who would be in the company would be using that? And is it possible for them to, those users to interact more flexibly or dynamically by writing their own queries, or something that, intermediate between the most complex type of query and just writing sort of ad hoc things with a tool or something?
Yeah, so the users within the company are basically our marketing science group, which is a group that works more, I guess they're closer to the customers than product analytics is really, and they do a lot of, when a customer requests an analysis, then beyond our standard analyses that we have a pipeline for, then they'll go and run that. And they are also running these queries for against the UI. So that's who's using it. And we do have plans to make a more flexible API so that they can more easily interact with this programmatically as well if they need to have something beyond what's the standard analysis there.
And a second quick question, can you use this to recreate Pokemon Go?
I think you might have to have more graphics than we have to have Pokemon Go. But it would be really great to have their data.
All right.
So my question is, do you include the time attributes in the data? Like the time you try to tag is the spatial temporal data set. How do you solve the high dimension curves? Like I have experience on the climate data set, try to predict the hurricanes in the North Atlantic. So we have nightmare about the high dimensions because the sliding windows. You need to have different combination of the time, location, and the time. How do we solve this kind of things?
So thankfully, we're not like trying to predict hurricanes here. So there's a little more, and nobody's life is in danger. But so we can do things like aggregate up over a day or hour, so that we're not dealing with as high dimensionality as you are. So we don't need to know exactly what second a hurricane is going to hit. So I'm afraid I don't have answers for you there.
I'm glad you don't tackle the hurricanes because we take a look at all years, several years. We have all the locations in the globe, so there's lots of the data set at highly dimension. So just nightmare. Don't do that. Thank you.
A quick question. At any point, was a traditional load-balanced, clustered, traditional database management system an option for the back end for any piece of this?
You mean like a SQL database, or?
Exactly.
So we've kind of used a hybrid. A SQL database is not necessarily the best thing to use with Celery, although we have tried that. But we wanted to make sure that if multiple users submitted, then we wouldn't have a problem, and so that was our solution. Does that answer your question?
I think so.
Any other questions? Cool. Well, thank you, Alice. This was awesome.
Thank you.